Hello and welcome to today's session. Today's topic is related to the hatchet I have here. We will see in a few minutes. To today's topic. As first, I want to do a little test with you. Imagine Origin without a cutter. What do you see when you imagine Origin without a cutter? Well, this is what I see. It's a brilliant tool, brilliant software, but it can't get you anywhere because there is one main part missing. In this case, with the Tesla, it's the tires, and in the case of Origin, it's the cutter, which hopefully isn't missing. So, yeah, we have a strong need for a cutter in Origin, and what you see in the camera are the cutters we have in the past thought that they're good for Origin, and that's why we took them in and added them to our shop. But how actually do you see if a cutter is good for Origin, or how can you determine if a cutter will work well with Origin? This is our topic today. So to start, first, because some of you may not be familiar with the topic, we will begin with the basics. When we have a look at a cutter, like for example our 16mm pocketing bit, then we can see that it consists out of two main parts. We have the shank and we have the head of the router bit. So the shank part, pretty easy, just a round from 8mm or less. 8mm is the highest diameter you can insert in Origin. That's just because of the collet. When we have a look at it, 8mm is the biggest diameter which will fit into this collet, but it's also possible to have the lower numbers, such as, for example, an 1/8 of an inch, which looks like this. And in this case, we can also insert other cutters with a shank size of an 1/8 of an inch. For example, this really small roughing bit. And yeah, on our side, for this case, we have the collet kit with all sizes from 8mm and lower. So 8mm, 1/8 1/4 of an inch, an 1/8 1/4 of an inch, 8mm, 6mm, and 3mm. Okay. One other thing about the cutter shank is the small engraving you can see when you have a close look to it. Then you can see here is the engraving like K, and this just means that it's the mark where you have to clamp the cutter. You can insert it more into the clamp, but you shouldn't pull it out more. You shouldn't see this completely when the cutter is inserted in the collet. That's just that you have enough clamping force and the cutter won't fall out of the collet while you're cutting. Then on the other side, when you take another example, on the other side of the shank we have the head of our router bit, and the main parts of this head are the flutes. In this case we have a straight flute and even an exchangeable one. but there we are also very variable. When we have a look at these colors, for example, then we see we can have something like this, an up spiral. This is our 8mm bit, and this is basically the same geometry, but not with the regular flutes like this one. This one here has roughing flutes, so it will break the chips when it cuts the chips, and due to that it has less cut force and can cut more material in one go. But also it will leave a serrated edge, which you have to clean up with a finishing bit in the end. There's another example, or another thing you can have. These two are with a positive spiral. That means that when this rod bit turns, that it will extract the chips to the top of the surface. And if this is a negative spiral, so the other way around, then the chips will get it extracted down, so to the bottom of the workpiece. One thing you have to consider when you have up or a down spiral, then the chips on the edge, like the fibers on the edge, will also get pulled up and can stand up on the edge. So if you have a lot of fibers you have to sand down, you may have to take a bit with a straight flute or a downcut bit, or you just have to sand it. That much to the flutes. So the side flutes. We also have another flute on the cutter, which you can see when we tilt it a little bit. It's the really small one here on the top. This is the bass flute, and this makes sure that you actually can plunge with the cutter. With Origin, it's better if you have a router bit that can plunge in C directly without having to ramp. And in this case, you should make sure that your router bit has flutes which go to the middle, like here. You can see 3 flutes, all of them meet in the center points of the cutter, and so this one cuts on the whole diameter of the head. The other example here is a router bit with 2 flutes which do not meet in the center, and that's why we have a small part which does not get cut, and so we are not able to plunge directly into the material just in the C-axis with this one. It will leave this small area of material which just gets burned away. That much to the flute. Another interesting part of the cutter is when you have a look at this one, is the part where we have no flutes, like there where we have the chip groove. In this case you can see it's really shiny. This means that this chip groove is polished, which leads to the fact that when a chip gets extracted, it won't stick to the chip groove. Even if you have material like plastics, which tend to melt when the rotation, for example, is too high and they get hot, they can melt and glue up the cutter. And in this case, when you have polished chip groove, they're way less able to stick to it. Okay, that's one thing, the flutes, like yeah, how many of them we have and where they are exactly. But another very interesting thing is how they actually look. So I have an example here, like the flute of a hatchet and the flute of this cutter here. And you see the one of the cutter is really small, like has a really small angle at the tip, and this one has a wider angle. So this means they will cut differently in the same material. You can use the example when you go back to the Tesla. When you drive it in a snowstorm, you will need other tires than when you drive it in summertime. So if we use these two flutes on the foam we have here, you can see that they will behave differently. So with a hatchet, I have to get a lot of cut force, like a lot of pressure, but the flute doesn't really cut through the material. It just pressurizes the foam. And if I have enough force, I can push it through, but I won't get a really clean result. You can see the material here is completely compressed. On the other hand, when we use a flute, in this case, which is really thin, has a really thin cut angle, then we also have to apply a little bit of pressure, but this one cuts easily through the foam and leaves us a really nice, really clean cut. So you can say the harder the material, the bigger your flute needs to be, because when you have a hard material, you need more force to extract the chip from the material, and when you have more force on the cutter, you need a flute which is way more stable, so more a flute of a hatchet than one of the cutter here. The other way around, when you have very soft material, we need a flute which cuts really well, and the material will not give that much pressure, so it doesn't really matter if the flute is not that stable as the other one. Very good. That's what you can say about the flutes, but there's also the machine part. And when you go to Origin, to the cut menu, let's do it in English. You can see we have a cut diameter and offset like you know it, but we also have the speeds menu where you can set the speed for the plunge, like the C direction movement, and also the automatic speed, which is the X and Y direction movement. So you can say, or you can determine how fast you cut, like for example 10 centimeters of material. And this is the first variable you can change on Origin itself. The second one you see down here. There you have a small wheel for the rotation speed. So this determines how fast the cutter turns around itself, like how fast the spindle turns. And yeah, these are the main two factors you can change in Origin. What also has some influence is the cut depth, like how much material you take in one go. But yeah, we'll stick to the feed rate, like the speed and the rotation of the cutter. I've prepared a small visualization of this thing in my CAD program. So you can see here, the white part is our material. Let's say it's a centimeter in length. And what you can see here, the red parts here, like each point is one interaction where one flute extracts a chip from the material. So in this case, you see we have quite some interactions between the color and the material. And yeah, for sure, if we have a color with more flutes, like say one with 3, we have way more interactions because we have one flute more. So in one rotation of the rudder bit, we have, instead of 2 interactions, we have 3 or even 4. But let's turn this down to 2 again. What we also have here is the rotation speed, as shown before. So if we take this down, you can see the interactions get less, because in this 10 millimeters of material, we have automatic speed, which is stable. So the less rotations we have on the rudder bit, the less interactions we'll have with the flutes and the material. And so in this case, the chips which one flute has to extract will get bigger and bigger. On the other hand, when you turn this up, you can see that we have more interactions, and the chips get, due to that, also smaller and smaller. Then as the third variable, we have the automatic speed, like the feed rates in millimeter per minute. And you can see, if we take this down, like let's say instead of 3, we have 2 meters per minute, for example. And you can see the interactions get more because we have the same rotation on the same length, but we drive slower with Origin. So we have more interactions of the flute with the material. In this case, what you see here, when you have, for example, a rudder bit with 4 flutes and a really slow automatic speed and a really high rotation, we have a lot of interactions, really, really small chips, but also a lot of friction. And in this case, this will certainly mean that the material will burn, or in cases of metals or plastics, it could also melt. Then the other extreme, when you go very fast with Origin with automatic speed and very slow with the rotation, we have not enough interactions, so the chips get really big, which means that there's a lot of pressure on the cutter itself, and this leads to a really bumpy edge in the end. So the whole thing here is, with this 3, like let's say the rotation and the automatic speed, because the flutes you can't really change. With rotation and automatic speed, you have to find like the good middle for a certain rudder bit, that you have the chips not too big, not too small, and you can cut a really clean edge with it. I've prepared a little example here how this can look. For example, what you see down here is a very fast automatic speed, very slow rotation. So the chips which the rudder bit had to extract were pretty big, and it ran not really smooth, like it was very bumpy, and you can also see this on the edge here. It's absolutely not clean, and on this part even the flute hung into the material and the whole spindle got pushed apart. What you can see in the middle is like, yeah, the middle with good chip thickness, like a medium automatic speed, medium rotation, and you can see the result is way cleaner than the first one, and like the thing you want to have with the cutter. Then the third here is with a very high rotation, very slow automatic speed, and in this case you see that the wood begins to burn, and you can see that the edge turns black. In the worst case, when you have too fast rotation or too slow automatic speed, it can be that you have like a fire in the chips which are left in the groove, and if you suck this in with a vacuum, it may be that your vacuum will burn. That much to the rotation and automatic speed. Chip thickness and the flutes, or number of flutes and angle of the flutes, are not the not the only variables we can change on router bits, but they're definitely the most important, so we will stick to them and forget the others for the moment. So how do you actually choose a router bit for your application? So in the easiest case, where is it? When you have, for example, something like dovetails, double dovetails, as you can see here, it's pretty clear what router bit to choose. In this example, we need one which fits into the dovs. Like here. So it does not, or it could not be too big, otherwise it won't fit into the dove and it will cut too much material, and this one here wouldn't work. So if you have an application which is really special, you need a special cutter. But that's not a big issue, because most of the cutter providers or resellers, like Festool in this case, offer a little drawing which comes with a router bit, where you can see how big it is, if it will fit your application or not. And in this certain case, we also have a really big description of what materials you can actually cut with this router bit. In this case, it's wood and plastics. But yeah, the biggest range of materials you can cut with Origin, let's say between foam and hardwood, are not that much different in hardness. The only material which requires another flute geometry is aluminum or brass. But all the others you can actually cut with all of the cutters you can see here. I can recommend just to choose a cutter which is made for a certain material. If you have a lot to cut, like if you have meters and meters of material, then it makes sense to have a certain cutter for the material, but not really for small applications. well, this is the case when you have something like dovetails, like T-slots, or yeah, like a grip you want to cut. In the other case, it's a little bit more difficult. When you have just a cutout in material or you have a pocket, then you have way more options of router bits to choose. And I prepared a small example here on the workstation. You can see we have a sheet of wood. It's oak. It's 18 millimeters thick. And what we want to do here is a cutout. And in this case, it just needs to be fast. It doesn't need to be really precise or really clean on the edge. And in this case, we can, for example, take the 5 millimeter flute we have, which when you have a look at it, has a really large chip groove, so it will extract the chips very well, and so you can take a lot of material in one go. And due to this fact, we can take this material in depth because it's just a 5 millimeter cutter, so the diameter won't cut that material, and we can take it in the depth. So it's a 5 millimeter diameter. We have to reference the Z-axis with a Z-touch. And we're ready to cut now. As I said, it's 18 millimeters of material in thickness. We do it in 2 passes. The first one to 12 millimeter. And because we just have one flute, we have not that much interactions between the flute and the material. So we can turn up the rotation speed to make these interactions more. So we go to step 6 for the rotations, and for the speed we can choose something, I would say in the middle, around 450 millimeter per minute should be good for this case. But we will see in a second. So you can almost hear how good this goes, how well this cuts through the material, even if it's 12 millimeter deep. I barely can feel any cut pressure. And you can see we also have pretty clean edge. And yeah, a fast cutout because we can cut 12 millimeter in one pass. If we want to finish this up, we go to 19 millimeter, take out the offset, and just do the same thing again. I could have done even more automatic speed rate, like faster XY movement. To be even faster for this application. But you can see pretty well that this one works much faster if you can take more material in one go in the Z-axis. As another example, we'll do a larger pocket here on the side. And in this case, if we have a look at our assortment of router bits, it's definitely the 60 millimeter clearing bit, which due to its diameter takes way more material in one go. The main differences between the 16mm and the 5mm is not just the diameter, it's also the number of flutes. On the 16mm we have 3 flutes instead of the one which we had for the 5mm. And this means, due to the fact that we have more flutes, we will also have more interactions between the flutes and the material. And this means, to not burn our material, we can turn the rotation down a little bit, which also offers the benefit that the spindle has more force to cut the chips from the material. So we go down to 4.5 in step for the rotations. We create a rectangle. Which is a little bit larger than the one before. And in this case we have 60mm in diameter. A rule of thumb says that you can plunge plus or minus the diameter also in the depth. In this case 60mm will be a little bit too much, because it's also 60mm in diameter, and that's a lot of material to cut. So we go down a little bit to 12mm. We set the pocket and we'll try if these variables are set well. And you can see this goes way faster than, for example, if you had a 5mm. For pockets I really like to begin in the middle of the pocket and work the way out to the edges. This just because if you begin on the edges and work to the middle, you have a small part which remains in the end, which mostly breaks away, and then gets stuck up in the vacuum outlet. And then we're already finished with these pockets. Like you can see in the settings, 12mm deep. At depth you can't reach with all of the cutters in one step. But with the 60mm, this is exactly made for applications like this one. And you can see that we have a really, really clean pockets area. Like here. Imagine if we had done this with a 5mm, we would be here for some hours more. One thing I like to mention here is you can see it's really clean also on the bottom, which in this case is because of the flutes we have here on the top, which meet in the middle. They're actually made for applications like this and to get a clean bottom of the cutout of the pocket. So you see it's really important to choose the right router bit. You can you can go after the recommendations of your bits provider, or you can try yourself what works best for you with Origin. Our recommendations you can see here, and for sure we are working on extending these our assortment. Well, that was it for today for the topic Rabbit. I hope you enjoyed it and you learned some things more you didn't knew. And thank you and have a nice evening.